should work. Okay, so that worked out for the daily problem. Anybody have any major issues with that one?
Yeah, I did.
Plotting was just probably a huge pain in the butt.
I think I didn't convert well. Like,
This is your I hate writing in pencil. Noise makes me crazy. So what were you saying now?
I got the same plot for both.
Okay.
So I did something wrong.
In terms, because you got a different lambda max then?
Well, I got, like, the G.
Yeah.
I got the same curve. I got the same numbers. For
Oh, okay, yeah, so something must have happened in
yeah.
your Excel sheets, it didn't work out that way.
The syntax or whatever for the second one was horrible.
Yes, it was. I
I
screwed it
think
up
I
like
ended
5
it
times.
with like 5 parentheses. That was the last thing.
So just keep smacking it and eventually it'll work out. Cool. So last time we talked about the Bohr model of the atom, where again we've been like talking about that for a week. It feels like where we have the nucleus, we have those energy levels, electrons popping around it, and that's for hydrogen. The models that we use do change if you look at atoms with a higher charge, so you have to incorporate that atomic or that nuclear charge in there. So be sure to read through your book, double check that. You might want to include that on your next Quizlet exam sheet, okay? There's a problem with this though. What do you see as a problem? Well, what forces are going on here?
The Coulombic attraction.
Yeah, there's this Coulombic attraction, right? Okay, so there's that attraction there. What do like charges do what?
Okay.
I just want to
Oh,
get close.
like charges?
Oh, rebel.
Yeah, they repel. Opposite charges attract, right? So they go to the point where they start attracting one another. And like if I had a positively charged sphere here, -1 here, and let's say there's no friction, no gravity, what's going to happen to them?
We're just going to smack together.
Yeah, you're just going to smack together, right? To get that. Okay. Why doesn't it happen for this atom? I mean, really, this should be trying to get optimized to the point where the energy is lowest. The lowest point in energy would be where the electron and the nucleus are right next to one another, right? So why doesn't this happen?
I mean, because it's like sort of like a satellite around Earth, just because it's going so fast, you could explain it.
Yeah, it's going so fast that way or whatever. But if you calculate like the speeds of the electron, it doesn't like experimentally, if you do it, it doesn't work out to be fast enough to beat out this force. So something's wrong here. We can't explain it with what we have right now. To explain it, we have to delve into quantum mechanics. Before we do that, we have to talk about a bunch of mathematical stuff, okay? So what we're going to do today, we're going to spend today talking about the basic mathematics behind a lot of the principles we're going to use, such as wave functions. You guys ever heard of complex conjugates before? Maybe. Okay. We're going to be working with a lot of imaginary numbers too, which is fun. Yep, so if you've ever wanted to do that, that's what we're going to talk about today. So another way to express imaginary numbers, you know another name for them? Yeah, non-real. Yeah, non-real. There's also another one too. Starts with a C.
Complex.
Yeah, so that's what we're going to talk about. We're going to talk about complex numbers. And these are basically numbers that involve imaginary I. So numbers involving I. And do you remember what I was defined as?
Square root.
Yeah, square root. There's a reason we have to use I. There's a couple of functions where if you put I in them, and you take a look at that function squared, you get a real continuous function, which is beneficial. Okay, so we're going to ask an easy question. What is I squared then? Yep, it's gonna be -1, right? So I times I essentially, so square root of -1 times square root of -1. Those cancel out, you just get -1. Okay, then what's the value? -I times I. Yep, it's 1 in this case. We have -I times I, negative square root of -1 times square root of -1. We're going to get -1, which ends up equaling +1, right? Okay. Now let's apply that to a set of complex numbers. It's going to be important to know how to do this for something called the complex conjugate. Okay, so complex conjugates. So we're going to consider the following expression. We're going to say we have the function z. Z is going to be equal to x plus I times y. Okay, the way we denote a complex conjugate is we put a star next to it. So the complex conjugate of z star. That's how we're going to indicate that we're taking the complex conjugate of it. Basically what a complex conjugate is, wherever you have I, it's replaced by -I. So CI, you're just going to put -I there. Does that seem familiar to people? No, you might, I think you talk about it in linear algebra. The first time I encountered it was, maybe it was differential equations. Can't remember, it feels like forever ago. I do remember doing a lot of stuff with it in modern physics where we were talking about quantum and just a lot of weird stuff that you just like to poke and prod at everything and say, all right, math's weird here, let's check it out. Okay, so then what is going to be, what's z star then for our function?
X minus I1?
Yep. Okay. So then let's ask the question. So we have another function given, z is equal to 8 minus 3i. What is z star z? So the order at which you do this also makes a big deal for some functions. Most of the ones that we're going to see in class, it doesn't really matter if you take the complex conjugate of the first one or the second one, but to be mathematically complete, you should really always take the one on the left first, just by the way that it's written. If you're really interested in that, I'm sure somebody over in the math department can crow on forever about it. I don't care, I want to use the useful stuff right now. So we're going to have that, so that is our complex conjugate, right? All I did was just change I to -I. Then we're going to have 8 minus 3i. Okay, anybody, can you tell me what we're going to get? Yep, we're going to get 73. So the way that works, you're just going to FOIL it, right? So we get 8 times 8, which is what? Yeah, 64. Plus 3 times 8, I.
24.
Yeah. 24i minus 24i. Okay, then we're gonna get 3 times 3, so 9 minus I squared, right? The kind of good point of this is gonna become a real number as soon as we square it, right? These two portions in here, they go away. They're not really important anymore. Luckily, they have the same factor out front, or the same scalar out front, and then they end up just annihilating one another, so they're not involved at all. So the answer that we get out is going to be real. So in that case, yeah, it's 64. What does this become then? Yeah, positive 9. So like I said, 73. Much faster than I probably ever could have done it without a sheet of paper. Okay, so let's look at a couple more of these. In this class, we're going to be dealing with a lot of sine and cosine functions. That's because we're talking about waves. And everything's waves. Everything that actually, every function can be described as a combination of sine and cosine, which is weird. That's what Fourier transforms do. What was that?
I definitely learned that one.
Oh yeah, did you guys actually go through the mathematical rigor of a Fourier
I
transform?
think Kluznik kind of tried to one day, and none of us were listening because it was differential equations and.
Yeah, I don't think I retained it, but definitely wrote it down.
Yeah, if you can do it with a plotting program. I think that's the best way to do it, where you just keep padding more and more functions in, and you can watch it change from like something that just doesn't look right to something that matches. It's like, what the hell?
Yeah.
So I've always wondered, like, you didn't talk about it in instrumental analysis.
It was pretty much like you get this and it comes out as a wave, and then a lot of math happens.
Yeah.
Transform, and then you get this, which works.
Yeah, and then you get something that looks right. I want to know the people who first took like those like radio frequencies and all that stuff and Fourier transformed them into something that at the time they didn't know would be useful. Like,
I feel like they should get more credit.
they should, really should.
Something to make spectroscopy possible.
Oh yeah, exactly. And then you have the people who did like X-ray crystallography, who were like in a strange mathematic world, and they were just like playing with math. And one day they're like, "Hey, I bet you we can apply this to crystals." And then, like, it used to take an entire PhD to solve a crystal structure. Now you can do it like seconds with an instrument that's like on a bench top. It's crazy. So. Well, and they were doing it, like, they were taking pictures of Polaroids and then being like trying to line them up and figure out what was going on too. They didn't even have like anything digital. It was like legitimate film. So most of the old crystallographers, if you ever talk to them, they're also big photography buffs because they had to do that sort of thing.
Interesting.
Yeah. Reminds me of one of my professors I used to have. He was, his name was Tom Janik, but there was also another Janik. Like, so there were two Dr. Janiks in the chemistry department at Fredonia. They weren't related to one another at all, which is funny. So one taught organic chemistry and one taught inorganic chemistry. So we called one inorganogenic and one organogenic. So that way you knew exactly what you were talking about. Right, same
Works really
mustache.
well.
Yeah, it did. It was funny though. Like, then that's not even a common name. Okay, so we're going to look at one function that's combination of cosine and sine. And I promise you, those are the only trigonometric functions we're going to look at. I will never ask you about tangents. I will never ask you about cosecant, secant. No one uses cosecant and secant. And if they do, they're probably doing nothing of value. Or, and watch, they do something that ends up like solving all the world's problems. That's probably where it is. Hidden in, yeah, it's all hidden in cosecant. Okay, so we want to look at our function. We want the complex conjugate times that value. Okay, so what's going to be my complex conjugate of this function? Yep. Okay, now I need to multiply that by just a regular function. Okay, what are we gonna get out of that one then? Yeah, it will end up being 1 if you want it to be.
Cosine squared.
Yeah.
Plus.
Yeah, it's gonna be cosine squared.
Chunk that goes away and then plus, well, minus I squared sine squared, which is plus sine squared.
Yep, exactly. So let's go through the steps to show what happens. So we get cosine times cosine, right? So that ends up being cosine squared as a function. Then we're gonna get plus I sine x cosine x minus I sine x cosine x minus I squared sine squared x, right? And again, what happens to the imaginary components?
They go away.
Yep, they go away, which is really good because what we're going to see is this is related to the wave function. And when you look at the wave function squared, imaginary stuff goes away, which is good because if things are imaginary, we can't measure them. Sometimes. If you ever look at optical rotations, it gets really weird there. You have to take you have to take the imaginary component of something and then it translates to something real. I feel like something is heavily broken there. But okay, so we multiply that through, you get cosine squared x, then I squared, that's going to be -1. -1 times -1, positive. And then, just like James said, you can make that 1 if you wanted to.
I feel like I got a bad rap when it got named.
What's that?
Being called imaginary kind of isn't fair to I.
Yeah,
Because it is a thing. It's not made up.
it's not made up, but
It's not real.
did you know about the creator of Alice in Wonderland? Do you know much about him at all?
A little bit, yeah.
You like drugs a lot. What's that?
He's on acid.
Yeah, he was. What he actually was, it was in mathematics, and they had mentioned, like, they were first discovering I, and he was like, no, I is full of crap, I hate it. And he's like, I'm gonna write a book if I existed, and all these, like, stupid things happened. He was a mathematician, and he was so mad at the idea of I, he wrote a children's book about how ridiculous it would be.
Wow,
Is this
worked out
before
well for him.
It worked out real well.
Was this before the Euler identity?
I think so.
Yeah.
So,
That
or
was-
while it was being discovered. So yeah, that changed a whole lot too. All right, so do you want to do one more, or have you had enough?
One more.
All right. So given the function, we're gonna say f x is equal to -x over I. What is complex conjugate of f times f? Question mark. Okay, so what's the complex conjugate going to be then?
Positive x over I?
Yep, positive x over I, and we just have -x over I. What's it going to work out to be?
Negative x squared? Positive x squared.
Yep, positive x squared. So let's show it. So we're going to have -x squared over I squared. X squared, -1, right? -1's cancel out. We just end up with x squared. What I always do, I always write every step out, because if I don't, I mess it up. Or sometimes you're like, oh yeah, there should be a negative or a positive one there. I've done many, where you do many problems and you're like trying to solve everything, and then you're like, man, I got almost everything right, but the sign is off. And then you look back through it, and it's always because I just didn't keep track of it. Okay, so we're going to need complex numbers for this. We're also going to have to talk about eigenfunctions and eigenvalues. You guys remember much about those?
I remember everything.
They are a thing. What'd you say, Kinsey?
I said it might come back to me,
Okay.
hopefully.
You like matrices, right? Vectors.
Yeah, they are matrices. We're not gonna deal with matrices right away. We're gonna look at those further on down the line. We're gonna try and keep it as simple as we can and then move to the complex. That might be differential equations or linear.
I had them at the same time. I learned far more about them in linear algebra than in differential equations.
Yeah, I didn't learn much in differential equations. So the way it works is you have an operator, and it acts on a function. And you remember what you get out from that? So let's say, there's another one that we've seen this before. It's
Oh, you get something in the same function there?
Yep, exactly. So we're gonna get a constant or a scalar, whatever way you want to say it. We're gonna just call it a constant. And that same function. So the Hamiltonian operator is an example of one. It's a function that operates on our wave function. We get an energy out and that same wave function back. Okay, so to put it more generally, let's say we're just going to look at the operator b hat. B hat works on some function, gets us k times that function. So b hat is an operator. Y is considered an eigenfunction of that operator. So an eigenfunction. I have no idea why they picked like the German part first and the English part second. And then we have k. K is just just a constant, right? Okay, so let's look at an example of this. So we want to show that e to the ax is an eigenfunction it's going to be an O. Eigenfunction of the operator e dx. You show its corresponding eigenvalue. Okay. The nice thing is you always usually know what the function's going to be, assuming it is an eigenfunction of whatever operator you're looking at. Okay, so our operator in this case is e dx. What's our function is e to the ax, right? Okay, all we have to do is look at them operating, or looking at that operator operating on our function. We got dx with e to the ax. What are we going to get out of that? Yep, e to the eax, right? Okay. So that's our constant. That's our same function that came up, right? Okay, so we've shown that it's an eigenfunction. What's going to be the eigenvalue then? Yep. Eigenvalue is equal to A in this case. Okay, let's look at another case. We're going to ask, is e to the ax squared an eigenfunction? operator b dx. B dx e to the ax squared. What are we going to get out of that one? Yep.
2ax and then ax squared.
Yep. E to ax. Okay. Is this an eigenfunction then? See two people shaking their heads, no? Alex, you're shaking your head, no? Why no? Yeah, because there's a variable in here, right? So this is going to be our new function that comes out, right? There's x that's here, so the function is changed. So, yep, so that's our new function. So no! E to the ax squared is not an eigenfunction. Something to mention too is that operators always act to the right. Operators always act to the right. We're going to talk about a property called termination, where it doesn't really matter depending on where they go, but mathematically and formally, operators always act to the right of whatever function you're next to. So, for example, let's say we had b of x, some operator f of x. B is going to operate on which of these functions then? Yep, it's going to operate on f of x, then you're going to do all other mathematical manipulations. So it always operates to the right. Okay, do you want to look at another example of an eigenfunction problem? More complex one?
Yes, please.
Okay. Let's look at a combination of sines and cosines. So, given the function where psi of x is equal to a, which is just some constant, cosine n pi x plus b sine x, it's 0 or 1 probably, right?
No, I say we went 0 to 100 real quick.
Yeah. E to the x too.
Yeah, we went from something really tough to, or really easy to really tough. We're going to have two operators. Just first derivative with respect to x, and then we're going to have, do I b dx. So we're going to look at those two operators. Are we going to determine is psi of x an eigenfunction of q and I? So we're going to ask that. Okay, so for the first one, we just have to take the first derivative of that function, right? So we're going to have q psi d dx, all of this junk. A cosine n pi x plus b sine n pi x. Forgetting a parenthesis. Excel would yell at me. Okay, so what's going to be the derivative of that first term, that a cosine?
Negative a n pi cosine equals sine.
Yep. Negative a n pi times sine n pi x, right? Okay, what did you give the other part to?
Plus bn pi cosine.
Yeah. Pi cosine x. Yeah, okay, so remember you take the derivative of cosine, you get negative sine out, right? You take the derivative of sine, you just get cosine out. Oh, I screwed up. Should have put all that other stuff in. My bad. That all goes in here. Okay, now let's pull out some of the constants and let's see if we can find our original function. Let's pull out that n pi out. And what we're going to get, we get negative a sine n x plus b cosine n pi x. Okay, are we getting our original function out?
No.
No, we aren't. So is this an eigenfunction? Nope, it's not. So, an eigenfunction of q. So this is an eigenfunction of operator q. All right, let's look at d dx. So I hat, we said, was just second derivative with respect to x, right? Okay, we already have the first derivative. Let's just take a derivative of that. Does that sound good? All right, so we got d dx. What do we have? We had, let's just go, yeah, let's do that. n pi negative a sine n pi x plus cosine, oh, should be a b in there, n pi x. Okay, we're going to leave that n pi out front because it's being multiplied by everything, right? So we got n pi. What's going to be the derivative of this term then?
N pi times the first function.
Yep. N pi a. Well, what's it going to be?
So like n pi a cosine.
Yeah.
Well, minus.
Yep. There should be a negative sign up here, right? Cosine n pi x. Okay. What about when we take the derivative of that one?
Negative.
Yeah.
N pi a.
Yeah. Bn pi sine, all this stuff. Okay, looking at it real fast, do you think it's a eigenfunction? Yeah, it is. Let's pull out some stuff. Okay, what can we pull out from both of these terms?
Negative n pi.
Yep, so we're going to pull out negative n pi, so we're going to get n squared pi squared all times a cosine n pi x plus b sine n pi x. Okay. So yep, we get our original function back. This is our original function that we started with, right? Okay, what is the eigenvalue then?
Negative n squared pi squared.
Yep. It's negative n squared pi. x squared. So this is an eigenfunction then. So psi x is an eigenfunction. Of what we said I hat for this operator, right? Yeah. Okay. So you get that is. All right, so you get an idea or a feel for operators then. Okay, coming back to you. How much time do we got? We have a little bit. Are there any questions about eigenfunctions, eigenvalues, complex numbers? Because those are really important to continue on. No? Okay. All right, now let's start. I've shown this eigenfunction to you multiple times, and I just keep saying the wave function, the wave function, the wave function. We never really described what it was. We talked about what it was in inorganic a little bit, but we really didn't say what it is. So let's talk about wave functions and what's called the Born interpretation of wave functions. So wave functions and the Born interpretation. There we go. Okay. So what a wave function is it's just a mathematical function to describe the wave-like behavior of an electron. So a wave function. It's purely theoretical. So, mathematical function that describes wave-like behavior of a particle. What's the particle we're going to care about in this case? Yeah. For us, electrons. Okay. Wave functions, they have to meet the following criteria. Or at least there's consequences to these wave functions. The first one is they have no direct physical significance. 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 No. Yes?
Yes.
Yes? Okay. Looked wrong. So they have no direct physical significance. So you might be saying, why are we even bothering if they don't mean anything? Right? That's what I first said. I'm like, why do we have an entire class on this? We'll get there in a second. There is no direct physical significance, but there is physical significance hidden in there. All right, the other one is they must be continuous functions. Over whatever region we're looking at. What do I mean by a continuous function? Does anybody know?
Think of the actual, like,
You don't
actual
need
definition.
you don't need the super strict.
The vertical line test thing.
Yeah, exactly. You look to see if there are any breaks. So could you give me an example of a continuous function?
Let's just go with cosine.
Yeah. Cosine of x, if we were to plot that, let's say we're doing it in radians, looks something like that, right? That way. Sine starts at 0 and it's just shifted over. What would be an example of a discontinuous function or a not continuous function? There's also another,
Tangent.
yeah, it's tangent. It's a tangent. I don't know, I don't remember exactly where it does it, but it does these weird thingies like that. I screwed up that side. But it does something like that, where you reach a point, and as you reach that point, it just no longer is continuous. There's a lot of weird consequences for this too. People are using, so you know about refractive indexes, right? Where that's how, like how light reflects off the stuff. They're trying to use ideas about discontinuous functions to make people appear invisible. Have you ever seen the trick where you can make Pyrex disappear in corn oil?
Yeah.
Okay, I'll bring that in next time and we'll see that because that's fun. That's one I always bring, and I get like, so I'll bring it into classrooms and I'll get like adults who gasp and be like, "How'd you do that?" Like they'll interrupt kids, like go right in front of them and go like, "How did you do that? You are a witch!" Like,
Or like those little like hydrogel spheres.
oh yeah.
That like just soak up so much water, they're pretty much water.
Yeah, and then you can't see them at all. You can touch them and feel them and stuff, but it's fun. What I'll do is I'll bring in a Pyrex test tube. We'll have them break one of them, and then I'll dump the bits in, and then pull out like another test tube I had hidden in there, and it causes them to freak out. People don't know what to do. Like little kids are like, "Nah, you're pulling something," and adults are like, "How did you?" They get real perturbed.
I never thought of like using it for like a magic trick.
Oh yeah, that's all I. That's why I go into classrooms. I just get to do tricks the entire time. I feel like a magician. Okay, so the other thing that we have to have is it must have a continuous slope. Oops, continue a slope. It's another word that ticks me off because it's like 4 vowels right next to one another. It doesn't look right. It must be single valued. And it must not be infinite over the region we're looking at. Over a non-infinitesimal, so over really like, if we're not looking at like a tiny sliver of a function, non-infinitesimal, which I butchered the spelling. Nope, we're okay. All right, so over a non-infinitesimal region. So we're taking a derivative of something, and you look at it like as you approach that way and that way. Some functions might appear to be infinite, but over that really small region, we're not caring about it. Okay, so this begs the question, there is no direct physical significance of this. Why are we even bothering to talk about it? Question, if psi has no direct physical significance, why discuss it? It seems pretty pointless to do it. So, we've talked about wave functions. Let's talk about the Born interpretation. This is where we start to see the physical significance of this. So we're going to look at the Born interpretation for a 1D system. And what Born said was, if the wave function of a particle has a value of psi at some point in space, then the probability of finding that particle is proportional to psi squared. So let's write it all out. It's a lot of words, I'm sorry. The wave function, I'll shorten that. The particle has a value at some point x. Then the probability of finding a particle between x plus a small change in x is proportional to the magnitude of psi squared dx. Okay, after we explain what that psi squared is, oh, we're already way over, I'm really sorry. Yeah, so what that psi squared is, that's the probability, or the, in this case, if we're talking about electrons, it's the electron probability density. So that's why we talk about psi. If you take the square of it, you end up getting the probability density of an electron or a particle. Okay? All right, you have a Quizlet on Friday, right? I will provide you with any integrals you will need in a table. I'm not going to tell you which one you'll need, but you'll always have those for the exams, okay? So, write stuff down. We'll see you guys next time. Oh, I'll see you later today.